Déjenme decirles algunas cosas de él. Él es oceanógrafo físico con especialidad en la dinámica de meso y submesoescala. A través de observaciones, modelos y teoría, él se enfoca para entender mejor la dinámica relacionada con frentes oceánicos, mientras que su objetivo a largo plazo es mejorar el entendimiento de los océanos mediante el uso de los próximos satélites que van a venir, los cuales van a poder resolver la submesoescala, ¿no? El doctor Christian obtuvo su maestría en la Universidad de Johns Hopkins y su doctorado en oceanografía física en la Universidad de Rhode Island. Llevó a cabo sus postdocs en la Universidad de Johns Hopkins, en el National Oceanographic Center de Southampton, donde tuve el honor de conocerlo, en el British Antarctic Survey en Cambridge y en la Universidad de Bretaña Occidental en Brest. Ha recibido becas de Marie Curie, de la NASA, fue premiado por su mérito científico en el ONR y actualmente es investigador en el Departamento de Estuarios y Ciencias Oceánicas que pertenece a la Universidad de Massachusetts en Dartmouth. So, Christian, thank you very much for joining us. I'm very... gracias, gracias. So, it's all you. Go ahead wherever you want.
Okay, thank you, Sheila. It's very nice to be here. Thank you to Sheila and Alina for helping me with this Blue Jeans link website thing. So what I want to do today is something a little bit less formal. It should be more fun than simply just going through some equations and stuff, but it nonetheless is significant, I think, in terms of its impacts. Like it's theoretically, but also probably practically. And I won't have time to talk about everything, but feel free to, toward the end, to ask questions. So this work is sort of it's a big like thesis or a dissertation essentially in these first two papers, and then the third, which is on archive, so you can download it there. And then I'd like to just mention that some of the concepts in this presentation, I guess, have contributions from Xavier Carton and Grace Crystal. So Grace is a student at UBO in France, and a lot of her work was actually motivated to help her with her work, but unfortunately that didn't happen. And but nonetheless, you'll see some of her work in there. And then also thanks to some reviewers. So this research was funded by the European Commission. I had a Marie Curie fellowship to work with an individual in Brest, France, and this is a summary of that work. So by way of introduction, this is a thought experiment. Imagine you have a rotating table that is rotating at a constant rotation rate, angular velocity, and you have a fluid parcel in that tank. And now imagine that you placed a warm, buoyant source at the base of that tank. This can also be offset from the center of the tank with little effect on the dynamics, aside from viscous forces perhaps within the tank. So the question is, what will happen to this fluid parcel once you turn on this buoyant source? You can think of it as a candle or something in a fluid that's warm. But you kind of imagine that this buoyant parcel will move towards the buoyant source because of continuity. So the upward motion will result in incoming velocities, but it will soon start to feel the rotation of the tank. And so this is sort of a geostrophic adjustment problem. But in general, it depends upon the time and spatial scales of interest, as well as the intensity of the buoyancy source. So some relevant forces in the momentum equations include the Coriolis, buoyancy, and centripetal or centrifugal forces, depending on which side of the momentum equation it's on. And So today we're going to speak about a regime in which all three are important. Usually we talk about the first and second ones being important in the geostrophic case, but here we're going to talk about the third. So what do we mean by oceanic submesoscale? So horizontal scales on the order of 1 to 10 kilometers, time scales of hours to days, so near the inertial period. Gradient Rossby numbers near 1 or order 1. So here I'm defining the gradient Rossby number as the vertical component of vorticity divided by the planetary vorticity, vertical component of relative vorticity divided by the planetary vorticity. And order 1 gradient Richardson numbers defined as the vertical stratification divided by the vertical shear squared. Enhanced divergence and strain rates, enhanced vertical velocities, and instabilities that dissipate energy, modify stratification, and potentially impact tracer fluxes. So that's an academic kind of descriptive way of understanding, but what about a visual way? So this is a mesoscale eddy, a mesoscale feature off the coast of Madagascar. This is given to me by John Taylor many years ago. And then this is a submesoscale vortex on the edge of that mesoscale vortex. And so that's what we're describing as submesoscale. This is a model simulation by Capet, Xavier Capet. And here you have similarly a mesoscale vortex with submesoscale vortices on the perimeter. This is relative vorticity divided by the Coriolis parameter, or the gradient Rossby number. This can also be seen in early simulations by Liam Brannigan and co-authors. Here you have a mesoscale vortex and submesoscale eddying flows in between two opposite signed vortices, mesoscale vortices. And that you may ask the question, you see these submesoscale features in model simulations, but are they really present in observations? So at the present, we only have infrared and optical imagery and perhaps SAR, synthetic aperture radar, that tells us about the submesoscale. But you can kind of envision it by looking at sea surface height. So here, this is a study where we found a submesoscale front or filament-like structure in between two opposite signed mesoscale vortices. And so what's happening here is there's a convergence of flow of cold water here and warm water here, and that gives rise to a sea surface temperature front that then goes baroclinically unstable, or we think is baroclinic instability. And the kind of scales of these eddies in this satellite image in infrared are 6 kilometers or so. And so if you identify that frontal boundary, you'd find that was the kind of the scale of the undulations. So to place that into context, you can take a satellite imagery or satellite image of sea surface height. This is sea level anomaly, and I've overlaid the eddy tracks of Dudley Chelton and co-authors just to kind of highlight where the eddies would be. And so this feature, where the red and the blue are basically these eddies that you see in Dudley Chelton's eddy tracks. So you can imagine that these submesoscale features are just ubiquitous within the upper ocean. And there's a question, does this impact energy, buoyancy, and tracer budgets? And in fact, there's a lot of evidence to suggest it does. I think it's still an open question to what extent. So one of the hallmarks of submesoscale flows is skewness in the distribution of relative vorticity. And this was evident in a very large-scale field campaign called LATMEX in the Atlantic Ocean. Here the authors took two ships in parallel and estimated gradients of velocity between them and found that relative vorticity is in fact positively skewed, meaning that there's more cyclonic vorticity here than there is negative vorticity, although the mean is offset to negative values. So they then broke it up into strain rate versus vorticity and found two features. Here I'm defining the strain rate as shown in terms of horizontal velocity gradients, and the relative vorticity as traditionally shown in Cartesian coordinates. So they found two features. One is that strong positive vorticity approached a pure strain relationship, suggesting that, a pure shear relationship, suggesting that these were predominantly reflective of straight fronts or geostrophic fronts. So in contrast, so that's the first feature, sorry. In contrast, the second feature, negative vorticity values were weaker and had a higher probability of nearly solid body rotation. So that's an eddying-like structure. And so my interest in this is to kind of examine how vorticity is distributed and why we have these two features. So while there's many ways to discuss what I want to talk about today, previously I've talked about it in terms of symmetric instability, I decided to do something a little more fun, I guess, and discuss it in terms of this distribution. And it's more germane to previous work that I've done, let's say. So the first can be explained using PV conservation, this cyclonic tail, and the second has not yet been explained, but we'll try to explain that today. More generally, we'll try to motivate a more three-dimensional conservation theorem for the F-plane that's similar to Ertel. So I won't derive that today, but I will kind of like sketch an outline to it. So the outline of today's talk is a little tutorial on what shapes the distribution of relative vorticity, the stability, instability, and Ertel PV, what happens when centrifugal forces or accelerations are present, and then a simple conservation of vorticity equation. In fact, it is a vorticity equation for the F-plane. And then I'll try to conclude. So I'll just try to keep an eye on the time here. Does anybody have any questions before I get started? I guess maybe some of the... Okay. Okay, I'll keep going. So this is like a little tutorial on what shapes the distribution of vorticity. And actually, I think Shayla might have been here at the time I was doing this work. It's really originally given in a presentation in 2015. But it's basically a nice, basic kind of like simple explanation of why vorticity is skewed for straight fronts. So a number of distributions in the oceans can be Gaussian, temperature, velocity. It depends on the magnitude of the temperature, of course, but usually it's Gaussian. One exception in the ocean is relative vorticity. So here I'm describing the PDF, or the likelihood of relative vorticity. And if you divide by F, you can get rid of the hemispheric dependence. And you can see that it's bound at -1. So the gradient Rossby number, or the relative vorticity divided by the planetary vorticity, is bound. But it's not bound in the cyclonic direction. So most of the mesoscale ocean is characterized by pretty small gradient Rossby numbers. So we don't typically see this skewness. That's why it requires these submesoscale measurements that people have discussed. And to date, there's only 3 studies that have described the skewness of relative vorticity, to my knowledge, in the ocean, in the upper ocean. I won't discuss those, but it's good to know that they all occurred in winter too, by the way. So what shapes the distribution of relative vorticity? So again, this is very basic, but it brings us all on the same plane, and it's kind of a good, fun starting point. So consider the relative vorticity of a fluid parcel. Imagine that you have a flow field and you have a fluid parcel in that field. It gets advected along and it feels different velocity values or gradients in U. And so spatial gradients cause rotation. In fact, relative vorticity is a measure of the rate of rotation. So now consider the same fluid parcel on a rotating Earth. Here you have relative vorticity divided by 2. So this is the rotation rate of the Earth and the fluid parcel. And the fluid feels a part of this rotation, so F over 2. So the total or absolute rate of rotation, and then that is essentially F plus zeta over 2. So then you can define potential vorticity, which we use the letter Q. It's F plus zeta over H, where H is the fluid height. In the absence of external forces, this quantity is conserved. And so it's very similar in a sense to angular momentum because H can change, and that changes zeta, or the spinning of the fluid. But it's actually different than angular momentum, and we'll talk about that in a little bit. But it's important to know that it's not the same. Nonetheless, we're often taught that it's the same in oceanography circles because it has the same sort of feel. But together with continuity, this implies that you can you can write a conservation equation for relative vorticity. This is a barotropic equation. The W is vertical velocity, and this dW dz represents a stretching. So if you could just kind of think about this for a bit, this is really simple, but it nonetheless is informative. So if zeta equals 0 initially, so at time t equals 0, and the stretching of the layer is positive, meaning it's going like this, it's stretching, it results in relative vorticity the same sign as F. That is, a change in vorticity is initially 0, except that if this is positive, then it'll increase zeta, and then that'll feed back, and so you have a positive value the same sign as F. And you can kind of imagine that this would keep growing in time. So eventually, you'll get something that's large in the same sign as F, or cyclonic. So cyclonic vorticity is actually unbounded. This is a barotropic vorticity argument. So what shapes the PDF of relative vorticity? Again, let's try the anticyclonic direction. So let's imagine we compress this. That actually gives rise to vorticity of the opposite sign of F. So if this is negative, rather over here, if this is negative, it'll cause this d zeta dt to be negative, and so that will decrease vorticity. And so you can see that over time, this value will become smaller and smaller until it eventually goes to 0 and you approach F. So anticyclonic vorticity is bounded. So what happens when zeta actually equals minus F? So you imagine strong cyclonic flow. You keep decreasing this until it's anticyclonic. And then when it approaches minus F, it actually gets there. It has potential for instability because it's not moving in an absolute sense, and so it's susceptible to little perturbations. So what changes the shape of relative vorticity in terms of the distribution? Recall that's the mesoscale, and at large scale we have the submesoscale. In essence, conservation of potential vorticity. That's what changes the distribution. Is that good? Everybody there? If you have any questions, feel free to ask. So some examples of these instabilities. You do have a question?
No. I mean,
Okay.
of course we have, but go ahead.
We keep going, yeah. So in general, like you want to do, this is a barotropic argument, but more generally you have to use conservation over tel PV for a baroclinic fluid. So we'll try to get to that. So there's a lot of talk about instabilities these days. I did do one of these Google Ngram plots where you can look at the frequency of books that display that have submesoscale in the term, and you see that it's exponential in the last 5-10 years. But what are they? What are these instabilities? So you can kind of imagine gravitational instability as a loss in heat or precipitation. It changes the buoyancy. You have centrifugal or inertial instability, although that's not correct for a vortex, and we'll see that in a minute. And we have types of instabilities when the PV is 0, but it's still stable, and like n squared is still positive, and zeta is not close to F. So that's called symmetric instability. So what is the connection to tel PV? We can use the work of Hoskins to kind of show this. So we expect instability when FQ is less than 0, where Q is the tel PV, and this is expressed as the absolute vorticity multiplied out. So this is the vertical component, and this is the horizontal component. And so we have n squared, the stratification, the horizontal vorticity, and the lateral buoyancy gradients. You can see from this, if this term gets close to 0, like what would do that? It would be when f is close to minus f, or when zeta is close to minus f, rather, or when n squared is 0, or when this last term is negative or small. So you can show that under thermal wind balance or geostrophic flow, that this term is always negative definite. So it always tends to reduce the flow. And when this part is important, when it's very low, it's described as symmetric instability. So these types of instability do not include baroclinic instability. And I should probably have included a Phillips reference here, but the general idea is it's not the typical undulations of the boundary that we're talking about. So you can also, by the way, divide by fn squared, f to remove the hemispheric dependence, and n squared just to, assuming it's positive. You can rewrite it in terms of non-dimensional numbers. So this is a non-dimensional Ertel PV. So here we have 1 plus the gradient Rossby number minus 1, the inverse Richardson number. So this is actually attributed to Hoskins. He showed this in his 1974 paper. So where does this connection to PV come from? Well, in a very heuristic sense, rotation of a fluid and stratification of a fluid stabilize the flow. And so Ertel PV is actually the inner product, or the product of rotation and stratification. So when that term is 0, when either of those terms or the inner product is 0, the rigidity of the flow to small perturbations, for example, due to internal waves, will be lessened and reduced to the point where you can have instability. So here I'm defining omega A as the absolute vorticity. Here's the relative vorticity. This is the planetary vorticity. And this is the lateral density or buoyancy gradients. Okay, so that's a heuristic explanation, but where does it really come from? A nice way to get at this is through this Sawyer-Eliason equation, which essentially describes the overturning stream function, psi, in a front. So you examine the response of a geostrophic front to internal waves due to some perturbations, and then you assume it's constant density gradients. Here we're going to assume it's inviscid and constant velocity gradients as well. So your vorticity is constant, and your vertical and lateral density gradients are constant. And if you do that, here are the coefficients in this partial differential equation are defined. It's a second order PDE, so you can define it as having different nature based off the sign of these coefficients. It's elliptic or parabolic or hyperbolic. And the sign of these, or the magnitude of these coefficients determines this kind of state. And so the mean state of the front is actually described in this one equation. So the discriminant, is essentially proportional to the Ertel PV, and you can insert a modal solution into this and get the following. So basically, the Coriolis parameter times the Ertel PV has to be negative for instability. And this was first shown by Oyama and later by Hoskins. Although I'm sure people kind of knew about it before. But that's a good reference for you. So why is the distribution of relative vorticity positively skewed? First, we rewrite the discriminant for flow and thermal imbalance. So FQ, you can expand it as shown here, where omega H is the horizontal vorticity. So you can kind of neglect by scale arguments, you can neglect the vertical changes in the horizontal changes in the vertical velocity. And that gives you this expression, and lo and behold, it's negative definite. It's always negative. And then you can divide by f squared n squared, which is always positive, assuming n squared is positive, into this, and you get this non-dimensional number, which is the non-dimensional Ertel PV. And so for balanced flow, you can rearrange that inequality to show that it must be, the gradient Rossby number must be bound by -1 and the gradient Richardson number. And here I've defined the terms on the right again. If you look at this in terms of distribution, so you can start to argue that in wintertime the gradient Richardson number is low, so that the inverse gradient Richardson number becomes important. So this is kind of what I'm depicting here, is a PDF of the gradient Rossby number, and you can see in wintertime it pushes the gradient Richardson number, or the inverse gradient Richardson number, pushes the distribution over, so the skewness becomes more prevalent. So we see that in observations, and we think this is a good argument for why vorticity is really positively skewed. So you can also do this in non-dimensional space in terms of a regime diagram. So gradient Rossby numbers on the y-axis, gradient Richardson numbers on the x-axis, and you have reduced stratification as you go to the left, or increased vertical shear. So we're talking about Richardson numbers near 1. You can see that it's very heavily cyclonic. Okay, so and it's not so heavily, because you would expect unstable flows not to be observed. That's the argument there. So this is a result of Hoskins, but all of this theory assumes thermal wind balance. And so my co-authors and I started to ask the question, if you look at the ocean, you see vortex flow or eddying flow and curved fronts, wouldn't a gradient wind balance be a better local approximation, at least, for these small horizontal scales? And that's pretty compelling, because the gradient wind balance, which is cyclogeostrophic flow plus hydrostatic flow, includes the geostrophic balance as a limiting condition when the curvature goes to 0. So when does this term matter is basically the question, and how does it change the dynamics? So the geostrophic or thermal wind balance is shown here. A cyclogeostrophic or gradient wind balance is shown here. You can derive the same overturning circulation for a front and gradient wind balance, which we did in our papers. It was first done, I think, by Eliasson. And when you do it, you find that the hyperbolic condition has this extra term. It's not just FQ, it's 1 plus CU. So this was kind of shocking to me when I did it, and it kind of makes the question is, what is the CU term? So here the CU is, you can think of it here actually. If you just factor out F from the parentheses, you have 1 plus 2V over FR. So this becomes a non-dimensional number, which I call the curvature number. So it measures centripetal accelerations, essentially. So where does this thing come from? So Rayleigh in 1917 showed that for an axisymmetric vortex, this conserves what he called the circulation, or the angular momentum of the flow. So here we have a substantial derivative of RV, and that's 0. One can also show, for example, in Kloosterziel and this other paper, that the same vortex flow on an F-plane conserves absolute angular momentum, meaning that you consider the planetary portion, or the rotating tank portion of the angular momentum, and that's given here. So L is absolute angular momentum. And then, without too much work, you can kind of scratch your head a bit and find that 1 plus CU is actually, if you just divide by FR squared, you get a non-dimensional form of absolute angular momentum. So just as 1 plus RO restricts horizontal shear, the conservation of vorticity constrains this term. 1 plus CU restricts centripetal accelerations. So we're going to call it L prime later on. But basically, the conservation of absolute angular momentum in a vortex or a vortex flow, a highly curved front, requires this to be conserved. So then you start to ask the question, what exactly is this absolute angular momentum? And I spent almost a month scratching my head over this in terms of its on the sphere. So for vortex flows, or any flow actually in this case, we can also define a quantity called absolute angular momentum. It's like vorticity in the sense that it has relative and planetary components. So we have r cross, so it's like a torque, r cross the absolute velocity, which you can expand in two components, the relative and the planetary. So r cross u and r cross omega cross r. So this is the planetary portion. So here we have a circular, so imagine a fluid parcel with a centrifugal acceleration, or a centripetal acceleration rather, on the Earth, and put it at the pole. Then r is this term here, ma is a vector quantity and it's directed upwards, and u is the relative velocity, and omega is the rotation rate of the Earth. Okay, if you just looked at the vertical component at the pole, you can expand it out and find that it indeed is what we thought before from the Klooster-Zeil et al. Type papers. So we have RV, where now v is the azimuthal velocity, and little r represents the velocity perpendicular to that plane. And omega r squared is the planetary portion. So it's basically the same, it's just that now we've isolated the vertical component. You can do that all the way down the Earth if you like, as long as you do it over the axis. And so this is what people call a polar vortex often. It's also valid away from the pole, but when? It's valid when you consider it at small horizontal scales. And so that's what we do here. So it's kind of weird because we're not taught this in oceanography, but it's in the literature for the atmospheric community. They usually talk about this, and they can also conserve this quantity instead of PV, and you get similar dynamics. But because it also applies away from the poles, we have to consider it here. So how do constraints on absolute angular momentum modify relative vorticity? That's really it's the question here. So if we let L equal the vertical component of absolute angular momentum equal that, then the conservation of the quantity demands that for an initially positive value L, for example, in the northern hemisphere, the absolute angular momentum must be positive for all future time. So we then can multiply by F to get rid of the dependence and just say, okay, now let's divide by F squared R squared, which is always positive. And so we get the scale argument that says that the Rossby number, or the bulk Rossby number, is bound by -1/2. So this is a bulk value, but it nonetheless demonstrates that vorticity has a bound on it simply because of constraints on L. So it represents a bound on anticyclonic vorticity. And one sees this when examining the stability discriminant. So I'm not going to go into this, but I've thought a lot about it. If the vertical component of vorticity, F plus absolute vorticity is F plus zeta, can be derived as this, the radial gradient of L divided by 1 over R, you can imagine a more general definition of absolute vorticity that's derived from the vector quantity ma, not just the vertical component. And so you really have a vorticity generating function here. So this is kind of like statistics when you talk about moment generating functions. Now we have a vorticity generating function, and it creates this unique set of vorticity. Okay, so that as an aside, so we basically kind of understand now where this 1 plus Cu term comes from. It comes out of the fact that Rayleigh showed, and then so forth on a rotating table and a rotating Earth, that this quantity 1 plus Cu is important for centrifugal forces, and it relates to conservation of angular momentum. So this raises a question in my head, or it did raise one, and I think probably for other people as well. If a conservation equation exists that connects to geostrophic flows, why is there not a single conservation equation it's not Urtel PV, why doesn't it exist for highly curved fronts or curved baroclinic flows? That is, the discriminant here must be positive for stability, and here it must be positive for stability, but we don't have this extra term in here in this equation. It's not just the conservation of Urtel PV. Moreover, it suggests that the discriminant divided by f is actually a better indication of possible vorticity values at the sub-mesoscales, and we'll get to that in a minute. In the limit of no curvature, it also reduces to Urtel PV. So can we make a quick argument for this equation? And so I'm not going to go into the detail, but essentially what I've tried to do in a very simple sense is conserve three quantities: mass, absolute vorticity, and absolute angular momentum. And I did that correctly, and I found so that these first two are conserved by Urtel in his 1942 paper, and that gives rise to Urtel PV. But if you include this third quantity, you get a different form of PV. It's no longer just the Urtel PV. And so the question is, what is that? I did it only for the vertical component of MA, but it does lead to a more general framework. But I haven't done that. So here what I'm illustrating is kind of a Venn diagram of these three conservation principles. And Urtel kind of describes this, but I describe this one little segment here. So one important point is that this quantity here, L, is conserved only on the F-plane. And this contrasts with a paper by Yeager, where he suggests that it is not conserved on the F-plane, but it is. But he was also interested more in the beta plane, so that might have been why he said that. So in a simple sense, you just can rewrite this, expand this term, and you get two very long expressions. But there's probably a more elegant way to do this. I just did it for illustration purposes. That if you conserve PV, and those are the first three there, and you conserve absolute angular momentum, which are the last three, then you can conserve this quantity LQ. And so this is written like Podlosky basically wrote in his textbooks for Urtel PV. But here I've had to learn all about absolute angular momentum and when it's conserved and when it's not. So for example, if you're near a seamount, it might change the gravitational field so that there's a torque on the fluid. And so that doesn't conserve absolute angular momentum anymore. And similarly, pressure torques, such as the undulations under an ice bed or something, if you had a vortex near ice or winds perhaps, would affect these. So, but nonetheless, if you imagine that you're not away from, you're not near seamounts or boundaries, you can imagine all these to be zero. And if that's the case, then you can write this simply in terms of the discriminant, the stability discriminant. And so for a fluid parcel in a vortex, it implies that it must be conserved. It's not necessarily true in a curved front, but in a vortex, this is true. So for an initial positive psi, you can imagine that psi must be positive for all future values. So this is kind of where I'm getting to the skewness part of the vortex flows. So if you do that and you conserve that quantity, you find that it's positive. So we can then, let's see if I missed anything. So that is for future states, the discriminant will be positive. Yeah. So you can rewrite the stability discriminant in non-dimensional form. So first you expand it, 1 plus Cu times Fq. This is for cyclogeostrophic flow. And you find that it can be written in non-dimensional form in this simple expression. 1 plus Cu, 1 plus Ro, minus 1 plus Cu squared, multiplied by the inverse Richardson number. And you can already see that if Cu, the curvature of the flow, is 0, this reduces to the expression valid for geostrophic flow. But nonetheless, that requires psi for vortex-like flows to be, or psi prime, to be positive. And you can I can show you that because Cu and Ro are related, it's quadratic in the gradient Rossby number. But don't worry about that for now. The main point is that this is the resulting stability regime diagram where you have Richardson numbers on the x-axis and Rossby numbers on the y-axis. So in non-dimensional form, you can see that it's stable for this kind of regime here, for a lot of the cyclonic flow, whereas it's unstable in the anticyclonic flow. In fact, so that's cyclonic above here and anticyclonic here. You can imagine reduced stratification. And this line here, basically 1 plus Cu equals 0, this line corresponds to the bound on vorticity that we talked about before. So this is true for a Gaussian vortex with a certain ratio, a Gaussian vortex at the radius of maximum velocity. But those are details that we can discuss offline. But the main point is that for low Richardson numbers, you get unstable cyclonic flow and stable, although weakly stable, anticyclonic flow. Right? So that's kind of weird. It's like opposite to what Hoskins had predicted, or Hoskins type theory would predict. You have now a stabilization of anticyclones. And it has to do with the tilting of the vorticity vector away from the vertical, and how that stabilizes anticyclonic flow and destabilizes cyclonic flow. But that's kind of complicated to discuss right now. But nonetheless, if you take them both, you have destabilized anticyclones under the geostrophic regime and destabilized cyclones under the cyclogeostrophic regime. So this might be an explanation for why you have more anticyclonic flow, although it's bounded by this L conservation. Why you have more anticyclonic flow for vortex-like flows. And that one, you have more cyclonic flow for straight flights. So that's essentially it. I should say that this was actually the idea I had in mind when I approached my co-authors a long, long time ago. But it kind of, it's a long story, but it morphed into investigating symmetric instability in the previous two papers. So the predominance of cyclonic vorticity for geostrophic fronts is explained by conservation of PV. And now the predominance of anticyclonic vorticity is explained by conservation of LQ in this study. So contrasting this with statements by Eager, we find that absolute angular momentum is actually conserved on the F-plane. It converges. It's both rational and consistent, to use the phrases that describe the mathematics. It converges to the equations on the sphere. Those are terms coined by Grimshaw in 1975, I believe. So a new conserved quantity is potential momentum. So I called it potential momentum just because I didn't want people to get angry at me for using sub-mesoscale potential vorticity. But you could maybe describe it that too. But the argument is that potential momentum, the baroclinic nature of the flow kind of allows momentum to change, just like PV was changed before. So angular momentum, that is. So returning to our thought experiment, we only have a few minutes. You can ask the question, what will happen? So instead of a geostrophic adjustment problem, now this fluid parcel comes in, and it's a cyclogeostrophic adjustment problem. I hope that makes sense. That now, depending on the intensity of the buoyancy source, this will have centrifugal forces in it that are non-negligible. So Cu will be much larger than 0.1, for instance. And that's when curvature effects become important. So a cyclogeostrophic adjustment problem. So this is kind of akin to Alex Stegner's work and Zeitlin's work using shallow water equations. So that's kind of neat. And it consists of two solutions. It's kind of like Gill, I guess, Gill's geostrophic adjustment problem. But here we have a balanced flow where LQ is conserved and unbalanced motion where this new form of PV, if you want to call it a PV, that it changes the way waves kind of disperse in the flow field, and also the way instabilities are stable or unstable. So that's kind of it. And I want to basically really highlight Grace, because she is not on all the other papers, and I've, despite my best attempts to get her on there. So this is her work on hydrothermal vent plumes. She's trying to model these with Krakow, and she has a buoyancy source and a velocity to the east here, or to the right of the page, and it produces these vortices, these which actually are sub-mesoscale in size, but nonetheless they have centrifugal forces in them. So this is really relevant to that. It describes all the dynamics near the vortex, ignoring some of the viscous forces, although the conservation equation still applies. And it also describes the flow as it goes away, and the trapping of tracers will be related to this as well, because symmetric instability will tend to move the tracers away from the vortex. So this is really her work, and I'm trying to do my best to say, hey, I'm sorry you're not on the papers. I really tried to convince my co-authors to put you on there, but it didn't happen. So I want to thank, before we close, the Marie Curie, the European Commission, Grace, a very sharp reviewer who I'm indebted to, who could have rejected the paper but didn't, and nonetheless didn't give me the answer either. So that was pretty exciting to discover it. And then years ago, discussions with those two people, George Nurser and Guillaume Roulet. Thomas Meunier, for recommending me to talk here, as well as conversations over the past couple of years. Charlie Desmarais, we worked on an early version of these manuscripts together, but unfortunately that didn't solidify, and then conversations with several people. And I'm also indebted to Amit Tandon for rescuing me over the past year or so. So that's it, and I'll just open it up for questions, I guess, if you have any. There you go,
Very much, Christian. It's a very interesting topic and, well, kind of hard to understand. But I think you give us a very huge explanation from the beginning. Bueno, pues abrimos sesión de preguntas para el doctor Christian. ¿Quién quiere ser el primer valiente?
A ver, Sheila, yo no soy valiente, pero ¿puedo?
Claro que sí, Luis.
Gracias. Hello, Christian. Thank you very much for your talk.
Hello.
A couple of questions. Well, because this topic of the skewness of positive vorticity it has been always very interesting. But our first question is, do you know what's the latitudinal dependence of this skewness? I mean, it's more important, it's more relevant in the equator or not?
Yeah, that's a great question. So F approaches 0 at the equator, so the skewness would not be important at the equator.
Right.
Because I guess of the conservation equation. Let's see here. Yeah, great question. I hadn't thought about it. Let's go back to this. It all depends on this. So if we can start to make arguments as to what F is and whether or not that really appreciably affects d zeta dt, then we can start to see skewness or not. So if F is very small, then probably initially the stretching won't matter so much in terms of changing the vorticity.
Yeah.
So that's,
okay.
I haven't really thought about it, but that's good to think about. Thanks.
Yes, the other question is related with the centrifugal instability. So do you think, I mean, this skewness of positive vorticity, can you relate it directly also with the centrifugal instability? I mean, in the sense that anticyclones are more prone to centrifugal instabilities, right? In the
Yes.
cluster style. So, is that a reason?
Yeah. Okay.
A reason enough to explain the skewness towards
Okay.
positive?
Yeah. So you would expect a bound here no matter what, right? That's kind of what you're saying. So if there's always a bound vorticity at -1, or F rather, -F, then you would expect skewness. That's kind of what you're suggesting?
Well, whether if one of the reasons is that anticyclones are more prone to centrifugal instability, as far as I understand.
Yeah, that is true because of L.
And the question is whether if that is a reason for explaining also the skewness on.
Yeah. So in a let's see, hold on. I have to think about that. I kind of hear what you're saying, but I guess what I've done is I've only examined it for low Richardson numbers. So let's take a look at two things. The first is, so these are the two discriminants that I'm showing here for geostrophic flow and cyclogeostrophic flow. So just for simplicity, you can think of this as straight fronts and vortex-like flows, or curved fronts or whatever. And so as you go to higher Richardson numbers, you get that bound exactly at -F of the gradient Rossby number, meaning it kind of asymptotes so that it's stable above RO of -1, but it's less stable below that. And then for cyclogeostrophic flow at high Richardson numbers, you get this weird phenomenon that you actually get more a stable flow here. So everything that I've talked about, I'm trying to assume low Richardson numbers because I'm thinking in my mind about the mix layer. So I'm not focused so much on this. So what this has to do with, we could talk about, but it's essentially when both absolute vorticity and absolute angular momentum are no longer conserved. They've both flipped signs, and then how do I show it? I don't know if I have it here. Hold on. They both flip signs, and then this term here, for large Richardson numbers, this term doesn't matter, and then these two terms become opposite in sign, but because they're both negative, they become positive, and so it's stable. So that's what's going on here. So yes, anticyclones tend to be centrifugally unstable, but that's because of the conservation of absolute angular momentum, as shown right here. So that does explain it, and I guess that's the point of what I'm saying, except that there, even then, you would expect more anticyclonic vortices, more cyclonic vortices than you would anticyclonic vortices. But in the present case, we actually see more anticyclones than cyclones in the distribution. So there's not so many cyclonic vortices, and you can show that by the strain rate versus vorticity plot. So this is kind of like the vortex flows in here. And there's more anticyclones is kind of the idea. I feel like I'm just going in circles.
Just a final question.
Yeah.
Would you say, I mean, your last expression in your last slide, I have to read your papers, of course. But
Yeah.
would you say that it is a sort of theorem equivalent to that of centrifugal instability? I mean, for the bottom. Right.
Yeah.
Okay.
Yeah, it's exactly that, except that.
But now, of course, including much more effects.
Yeah, I mean, it's like bigger than this. It's like an adjustment process.
Right.
You're conserving this quantity LQ just because of the Earth's rotation. And so when it's not conserved, due to frictional forces at a boundary, or due buoyancy effects, or frictional forces due to wind and things, it'll change this quantity LQ, just much like PV, and that'll tend to introduce instabilities. But yeah, it's essentially centrifugal instability in a stratified flow at low Richardson numbers.
Excellent. Thank you very much.
Yeah, sorry for the long explanation.
No, it's excellent. Thank you. Thank you very much.
Thank you.
Thank you, Luis. ¿Alguien más?
I also have a couple of questions.
Hi there.
I'm Julio here.
Hi, Julio.
A question and a suggestion actually.
Sure.
First, the question: has anyone? Well, actually, two questions. Has anyone thought about, like, non-traditional equations of motions applied to this kind of problem? Because I do wonder if you should consider, given these kind of ideas or scales, the other components of the Coriolis force, not just the vertical.
No,
but I've seen that obviously for internal waves, but I don't know if anyone has looked at this in the submesoscale regime.
Yeah, I think that's a valid topic to consider. I made the simple choice. So the equation itself, it's really a crude equation. It's a crude vorticity equation. So you can feel free to develop it properly, or more robustly and beautifully. But the basic sense is that if you assume that non-traditional effects don't matter, and then you get this nice solution here that exactly replicates the quote-unquote generalized Rayleigh criterion. And that's nice for my perspective, just because it makes it tractable. But in terms of internal waves, you're totally right. It's going to modify the dispersion relationship, and that would be really cool to explore. Future work, I guess. So not only does L modify the dispersion of the waves, but also the non-traditional stuff would modify.
Well, for internal waves has been done already, but it was wondering.
Yeah, it has been done, but only for the geostrophic approximation.
Sure, that's true.
And that's the work of Buckingham and
that's right. The other question is, usually, because what you are suggesting here is that, angular momentum conserves as a Lagrangian property, right?
Yeah, that's right.
Because generally, the way it's thought is in a way like an Eulerian kind of, like you have something plus a divergence, like energy, for example.
Okay.
So I do wonder, I guess it's more related with the suggestion, which we had a few years ago, Pedro Ripa, who was very well known in theoretical geophysical fluid dynamics.
Yeah, I've heard his name.
The Ripa's theorem on the stability of shallow water equations. But there are two papers on the JPO during the 2000 year. It's August 2000 and October 2000 on the dynamics of isolated things on the sphere, and he talks a lot about angular momentum and these kind of things, even on the beta plane, or actually some not approximations that he did on that go beyond the beta plane approximation. So you may want to have a look at those so JPO Ripa 2000 August and October.
Okay, great. Thanks.
Thank you very much.
Yeah,
very nice talk. Thank you.
Okay, thanks for the comments. Yeah, I vaguely remember that paper.
Gracias, Julio.
Yeah.
¿Alguien más? No sé si hay preguntas en el chat, en YouTube, o
Por
alguien
ahora
más
en
quiere.
YouTube no tenemos ninguna pregunta.
Muy bien. ¿Alguien más quiere entonces abrir micrófono y preguntar? Tenemos tiempo para algunas preguntas. Well, I have a question, Christian. Maybe
Yeah,
they're
Sheila.
silly questions, but especially with this plot, I was wondering the effect of these Richardson numbers. I mean, you put here unstable, so it means that even for larger Richardson numbers, larger than 1, the flow is still unstable.
And this plot up here where the cyclonic area is?
I was wondering about the anticyclonic part.
Right. Yes, that's correct. So all this, this is for a cyclogeostrophic, so it's a vortex flow. But where it says symmetric instability, that's when Ri is close to 1. When you go away to positive Ri, like really large or larger, you get to centrifugal instability. And that's because in this equation for the discriminant, this Ri term becomes less important because it's 1 over a larger number. And so this is centrifugal instability when you consider these two terms. It's a barotropic flow. And so yes, so the reason it's kind of a combination of inertial, which is the shear, and centrifugal, which is the angular momentum. So essentially, yes, anticyclones are all unstable until you get to really large Richardson numbers. Maybe I haven't looked at this asymptote here. At Ri of 4 up to 6, you can start to see stable flow. And so it's possible that in the ocean, when you're close to boundaries that give really strong frictional forces that spin it really fast, the vorticity of that, or sorry, that vortex that is really strongly anticyclonic may be stable. I don't know about that subject, but you can see it in this plot. And one of the reviewers kind of mentioned this like as a kind of a nudge that not that was possible, but that satisfies the Rayleigh criterion. Anyway, I'm not explaining myself well, but the gist is that it's anticyclones are all unstable up until some point in the Richardson number.
Okay, that's
interesting.
Sorry. And how, because I was wondering also what's happening in the mixed layer, for example, or the place where internal waves break and I don't know, I have to think about that. And of course I have also to read your papers. But I was wondering about the effects of this in the mixed layer.
Yeah, okay. I guess the best thing is to go to like the little diagrams. Like, right, so
yes.
So you can kind of imagine this as the upper ocean in the winter time, let's say. And so you'll have centrifugal or inertial instabilities. So so before I said that was wrong, it's because it's not just the shear, it's actually the angular momentum as well, the curvature. So it's actually a combination of two things. But anyway, and then you have the symmetric instability. I guess what will happen is if there's no curvature, then it won't affect, all this stuff won't matter. It'll just be like Hoskins and Stone type papers. Stone 1966. But, and then so forth with Leif Thomas and John Taylor and co-authors and Baylor Fox-Kemper. But if there is curvature in the flow, it's going to modify the balance of forces, and therefore things will start to change. And that includes the internal waves, but it also includes like how, so we often talk about PV fluxes, like into and out of the boundary layer of the mixed layer. Now we're going to have to talk about fluxes of LQ instead of fluxes of Q. So it also modifies like McIntyre and Haynes and McIntyre kind of theory. So that's one thing. So it's the waves and the fluxes. And what else can we do? Yeah, it's almost like it's just makes it more complicated for us. I didn't mean to do that, but I just sort of happened because when I was in review, I found out that I had the wrong answer. I started with a paper that said, imagine if Q is the discriminant, like FQ,
Okay.
and then it ballooned into this larger thing.
Okay.
Yeah, so like you, I need to think about it some more. But one of the things I was thinking about, and maybe this is good for your audience, is like if you had vortices off of Mexico, for instance, and the winds from whatever, fluxing, like the Tehuantepec or whatever, fluxing things off of the vortices, how would that change the dynamics? And is that important for various processes? And so this is one of the things I'm interested in, but I still have to think about some more.
Sure. I don't know if hay más preguntas. Que por aquí veo que alguien encendió su cámara y no sé si quiere preguntar. So, well, my last question, Christian, is did you mention that Grace working on this with a simulation?
Yeah.
I think it was. So did you try this on models and maybe, I don't know, observation? Would be great, but at least on modeling, right? Modeling studies. This is Croco, right?
Yeah, this is Krakow. So I think she's like considered it implicitly, like she started to do some stuff with it, her and her advisor. But because it's kind of new, they're more comfortable just using PV, I think. So they think of it in terms of that. There's someone on our committee named Bruno Durimbo. I think he's aware of my work and this work, and he probably is interested in this. He has a pretty well-known paper about buoyant convection and kind of related to the Gulf of Mexico. So but I don't think anybody has really considered this framework for like examining the flow and the fluid parcels. I'm starting to, so you ask a good question, but I'm not gonna, I have to kind of stay away from Guillaume and his student Grace's work, but I'm starting to examine it with Amit Tandon, some model simulations in the Gulf of Mexico, and there the vortices are really strong, and the meandering of the front, and all this curvature stuff matters. So I'm only examining it so far in the context of symmetric instability, but everything's kind of there, right? It's just an open, go get it. Like it's an open territory. I think the Southern Ocean will be a big one. Anyway, questions? I haven't done it from observations, no.
Okay. So there is a lot of work to do.
Yeah, one last thing that I wanted to say to you, because of your work behind the islands, you were using ROMs to examine island wakes, right? In Madeira, where was it?
Well, Canary Island, which is
Canary Island. Okay.
It's the same.
Yeah, so this is actually pretty applicable to that kind of stuff because
I know
there's vortex shedding behind the wake, right? And if you look at it a little bit more, you'll find that there must be some dynamic going on with the cyclonic versus anticyclonic.
That's right.
And I started to see that in some simulations that I looked at. But yours are much higher resolution and could be pretty cool to examine. So yeah, food for thought.
That's it.
Well, I should also say, Sheila, that you are aware of, not Sheila, that there is a group here working with gliders doing a lot of high resolution measurements in the Gulf of Mexico, which is where Shayla and I work as well.
The loop current stuff.
And the loop current, but also when all these loop current eddies go to the west, and so we are, or they are, I don't know if Enrique is here but they have been doing, and there is a recent paper precisely on submesoscale features on the rim of one of these one of these large eddies, actually, because it was a very strong one. So and this work is still ongoing, so there might be some data to check
that would be cool.
These ideas, actually, so that would be very nice.
Yeah, and we have also high resolution modeling in that place. It's a part of a big project. I don't know if Enrique is here. I think he's not.
Yeah, I'm here. Yeah. Yeah. Hello. Hi. Yeah. Yeah. There is this student, our PhD student, Juan. Maybe is also connected. He did some studies of instabilities across the large loop current eddies using glider data, but we did not use your new how you say the condition for instability. We use the classical Hoskins and Stone condition of FQ and minus F with the opposite sign to Q to PV. So, but yeah, for symmetric instabilities, we had a lot of problems with the glider data trying to see these conditions.
Because the Richardson numbers
going work, yeah, with glider, yeah.
Yeah, I'm a big fan of your work, actually, Enrique. I'm aware of it through Thomas Meunier a little bit.
We worked together quite a lot. Well, he worked more than me. he was hard worker during his postdoc. He's very efficient guy. So yeah, we all know Thomas. And also I know your work. I follow you also, and very nice theoretical development. Yeah, great.
Yeah, so when he was showing me a lot of his work with the loop current eddies, we were talking about this at about the same time because he was in France at the time. It's just I was kind of with COVID hitting and then everything happening in France, like for me anyway. There were other things that happened. So he left at about the same time, and it was kind of, we didn't talk as much when he went to Woods Hole. But we planned. Yeah, now we're very close.
We're very close.
Yeah, we should collaborate. I don't know. Yeah, if you want to discuss this another time, all this stuff. I mean, it could be your observations or just discussion to try to understand it more, or Kayla, I don't know if you want to talk. It could be fun. I could try to get Thomas over here.
Yeah.
Okay. Thanks, Enrique.
Thank you.
Thanks, Julio, for the suggestion.
Okay. So as a reminder, this talk will be online on YouTube, our channel. And Alina, if you can give me the link, because someone here is asking for the link in YouTube and also in Facebook Live. So thank you very much, Christian. Again, nice talk. I have to see you again to work together. We have models, we have observations, and to test this new approximation or this new form of vorticity.
Yeah, it's all weird to me, but I should say that it's all kind of been known in the atmospheric community, but they've never, I guess, I don't know, maybe the ocean community just has missed it all or something. I don't know. Anyway, but thank you, Shayla. It's super nice to see you again.
Sí.
And thank you for hosting me, and thank you to everybody. And Alina, thank you very much.
Yeah. In fact, Alina want to talk. Ella quiere dar un anuncio. She want to say something.
Okay.